The general formula for the $th term. Welcome, everyone. Let's begin our lesson on the general formula for the nth term. Now, if you recall from our previous subsection, we observed that to find any specific term in an arithmetic progression, or AP, we essentially find the first term and then repeatedly add the common difference to it over and over again. While this works for the first few terms, it becomes quite a tedious and time-consuming process if I were to ask you for the 100th or even the 1000th term. To avoid this repetitive process of adding the difference one by one, we are going to introduce a mathematical formula. This formula is a powerful tool because it allows us to calculate the value of any specific term in a sequence directly, regardless of how far along in the sequence it is located. In the next few slides, we will break down exactly how this formula is constructed and how you can apply it. 1. Defining the general term. Now that we've established why we need a more efficient way to find terms in a sequence, let's move on to slide 2, where we will formally define our notation. Imagine we are looking at an arithmetic progression, and we represent its terms as a sequence. A sub 1, a sub 2, a sub 3, and so on, continuing all the way to the nth term, which we call a sub n. To make our lives much easier and avoid writing those subscripts every single time, we use a simpler shorthand. We will denote the very first term, a sub 1, simply as a. Next, we have that constant value we discussed in the previous slide, the amount added to each term to get to the next one. We call this the common difference, and we represent it with the letter d. The value of the term at any specific position, which we call the nth term or the general term, is denoted as a sub n. Putting all of these pieces together, we arrive at our formal formula. To find the value of a sub n, you take the first term, a, and add the quantity of n-1, all multiplied by the common difference. D. This is the formula we will be using for all our calculations moving forward. 2. Understanding the components of the formula. Now that we have introduced the formula, let's take a closer look at the mechanics behind it. To use this formula correctly and avoid any confusion, it is essential that we understand exactly what each symbol represents. First, we have a sub n, which we call the nth term. It is important to distinguish this from the position itself. This represents the actual numerical value of the term sitting at the nth position in our sequence. Next, we have the letter a. This is our starting point, the first term of our arithmetic progression. You can think of this as the foundation or the initial value from which the entire sequence grows. Then we have n. This represents the position of the term. Now, a very important rule here is that n must always be a positive integer, such as 1, 2, or 3. In a sequence, you can have a first term or a second term, but you can never have a 2.5th position in a list. Finally, we have d, which stands for the common difference. This is the fixed amount that we add to each term to move to the next. Keep in mind that d can be positive if the sequence is increasing, negative if the sequence is decreasing, or even 0 if the terms remain constant. Understanding these four components is the key to mastering the formula we are about to break down in the next slide. 3. Why do we use $1? Now, you might be looking at the formula we just defined and asking yourself a very logical question. Why do we multiply the common difference, d, by n-1, rather than just multiplying it by n? It is a great question, and the answer lies in the pattern of how we build the sequence. Let's break down the logic step by really simple steps. Think about the very beginning of our sequence. To reach the first term, we haven't actually added the difference to anything yet. We are already there. So, for the first term, we add d 0 times, which we can write as a sub 1 equals a plus 0 times d. Moving to the second term, we have taken exactly one step forward from the start, so we add d 1 time. This gives us a sub 2 equals a plus 1 times d. If we look at the third term, we have moved 2 steps away from the first term, meaning we add d 2 times, or a sub 3 equals a plus 2 times d. Following this same pattern to get to the fourth term, we have added the difference 3 times, which is a sub 4 equals a plus 3 times d. Do you see the relationship emerging? In every single case, the number of times we add the difference is always one less than the position of the term we are looking for. Therefore, following this pattern, to reach the nth term, we must add the common difference, d, exactly n minus 1 times to the first term. This is exactly why that minus 1 is so crucial in our general formula. 4. Real-world application example. Now that we have understood the theory and the logic behind the formula, let's put everything we've learned into practice with a real-world application. Imagine this scenario. A student decides to start saving money in a piggy bank. In the very first month, they deposit $50. To build their savings, they decide to increase the amount they deposit by $10 every single month after that. Our goal is to determine exactly how much money the student will be depositing specifically in the 12th month. To solve this, we will follow a clear step-by-step calculation. Step 1, we need to identify our known values from the story. Looking back at our definitions from the previous slides, the first term, which we call a, is our initial deposit of $50. The common difference, which we call d, is the monthly increase of $10. Finally, the position of the term we are looking for, which is n, is 12 because we are interested in the 12th month. Step 2, we write down our general formula that we learned earlier. That is, a sub n equals a plus the quantity n minus 1, all multiplied by d. Step 3, now we substitute our specific values into that formula. So, a sub 12 equals 50 plus the quantity 12 minus 1, multiplied by 10. Step 4, next, we simplify the expression inside the parentheses. 12 minus 1 gives us 11, so our equation now looks like 50 plus 11, multiplied by 10. Step 5, we perform the multiplication. 11 times 10 is 110. Step 6, finally, we calculate the final sum. 50 plus 110 equals 160. In conclusion, by using the formula, we can see that the student will deposit $160 in the 12th month. As we move to the next slide, I want you to pay close attention, because I will highlight some common pitfalls where students often make mistakes when applying this exact type of calculation. 5 common mistakes to avoid. First, a very frequent error is confusing the variable n with the term a sub n. It is crucial to remember the distinction. N represents the rank or the position in the sequence, for example, saying the 10th term, whereas a sub n represents the actual numerical value sitting at that position, such as the value is 150. Always ask yourself, am I looking for the position or the value? Second, you might find yourself tempted to use n instead of n minus 1 in your calculations. You might mistakenly write the formula as a sub n equals a plus n times d. Please avoid this. As we discussed in our logic breakdown earlier, the first term doesn't have the difference added to it yet. We only add the common difference for the remaining n minus 1 terms. Finally, be extremely careful with sign errors involving d if you are working with a decreasing sequence. Remember that your common difference, d, will be a negative number. When you substitute a negative d into the formula, you must handle the signs with precision. Remember that adding a negative value is mathematically the same as subtraction. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the logic of the formula, it is very easy to make small errors that can lead to the wrong answer. Let's look at 3 specific mistakes to watch out for. Keep these points in mind as we move into our final summary. 6 key takeaways. First, remember the core of our topic. The general term of an arithmetic progression is given by the formula, a sub n equals a plus, parenthesis, n minus 1, parenthesis, d. This is the powerful tool we've been working with. As we discussed when we first introduced the formula, the real beauty of this equation is that it allows for the direct calculation of any term in a sequence. You no longer need to perform that tedious, step-by-step addition we saw in our earlier examples. You can jump straight to any position you need. Next, a very important rule to keep in mind for your calculations: n must always be a positive integer. As we noted earlier, you can have a first term or a 10th term, but you can never have a fractional position like a 2.5 term. Finally, let's reflect on the logic behind the formula one last time. That part of the expression, n-1, represents the actual number of steps or jumps taken from the first term to reach the nth term. It's the number of times we actually apply the common difference. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear. If you have mastered these points, you are well on your way to mastering arithmetic progressions. Great job today.